Mutual inductance is a principle that allows devices such as transformers to work. Transformers actually need AC current in order to work properly. But just as an introduction to that, let's analyze what might happen with a simpler DC source. As I showed in a previous video, coils take time to build up current. So even if we were to close this switch here, that doesn't mean that current would start flowing right away. It would build up slowly. However, the voltage of that battery would be placed across the coils. So the voltage starts high and the current starts at 0. Over time, the current will build up towards some maximum, and the voltage across the inductor will actually decrease. This is assuming, though, that the energy in the circuit is lost somewhere in these connecting wires. Over time, the galvanometer needle will progress from the middle to being deflected to the right. This is because current will be flowing. Now this cylinder could be made of some ferromagnetic material such as iron, where the domains of the material can align with the magnetic field created by this coil. And that can help transfer the magnetic field from one place to another. So once the current gets going in this coil, we're going to see a field through it. And the material will help that field penetrate through the other coil. The magnetic flux, however, is going to go along with the current. If there's no current, there's no flux. As the current increases, the magnetic flux increases as well. But now we need to come up with a possible graph for the EMF of the secondary coil. Now this should follow Faraday's law, which says that the EMF induced will be determined by the change in magnetic flux with time. Now if we look at the graph for magnetic flux, we'll find that it's approaching some limit that's getting closer and closer to a maximum magnetic flux. As it approaches that limit, the flux stops changing. But at the beginning, the flux is changing fastest. And so when it comes to finding the EMF induced, we want to start off with a large size of induced voltage. And we want it to be negative. It'll get closer and closer to 0 as time goes on. This shows that when the flux stops changing, the EMF becomes 0. When the flux is changing the most, the EMF has its largest size of value. So interestingly, as soon as the switch closes, that's when the voltage is going to be largest. Let's look at the coil itself and see if we can determine the direction of current. The coil will create its own magnetic field to oppose the change in magnetic field that it just experienced. And that would look something like this. There will be an induced field. And if we use the right-hand rule to figure out the direction, it looks like our current will flow over and behind our cylinder. So that means the current is directed in this way. So our second galvanometer would be deflected to the right as well.